Hello everyone, you're welcome to this lesson on MATLAB for Engineers brought to you by the GAD Academy. My name is Martin and I'm your moderator for today's lesson on vectors and matrices. Now earlier we made mention of vectors and matrices being the fundamental or the core on which the MATLAB programming language operates or is built. And it's very important that we get a good grasp of these concepts early on to smoothen our progress throughout the course. Now we are going to take it from arrays, which is the general name for all of these collections. And then we will look mainly at vectors and matrices within arrays, but we'll make a mention of some of the other collection types you have under arrays. So we start by discussing vectors. We'll look at how to create vectors in MATLAB, how to index or access positions of elements inside vectors, how to extract smaller vectors from a larger vector, carry out some vector operations, and then we will move to matrices and do same with matrices. Now an array is an ordered collection of values stored under a single variable name. Instead of creating separate variables for each value, an array holds all of them together in a structured way. So an array is used to store values. Right? Usually these values are related. So because of that relationship, they can be ordered. For instance, if you have a set of temperatures, all the values in that set represent temperatures. And since they have numerical values, they can be ordered in some way. So that is an array. So an example will be to take student scores in math in any subject. Now the recorded scores, if you were to record all the scores the students obtained, you would have an array, right? A list, because each score is related or belongs to a particular student. And because of that, there is an order, because the scores usually fall within a range. And based on that order, we can tell who performed best and who performed worst in the subject. So another case to look at is when it comes to arrays is that duplicates are allowed. Now, because the scores are related to or are owned by students, if three students scored the same points, for instance, if you have three students scoring 79, because the scores represent students or unique entities, you cannot merge all of them into one and just record 79 ones, because when you do that, you've eliminated two of the other students who actually have scores. But if you just wanted to show all the different kinds of scores that were obtained in the exam, 79 has already been represented once, so you do not have to show it, represent it again. So that will take what you have then as a set. So in this case, 17, 19, right, we have a duplicate here. All of this is an array of scores. Now the student with the highest grade will be first, and that score can be placed at the top or bottom depending on how the list is sorted. But essentially that's an array. An array is a list, a collection of values that can be ordered or that have some sort of order and are related. Now, if we were to force this into a set, if we're looking at the set, duplicates must be removed because sets looks at unique entities within a collection. So what happens then is once you remove the duplicates, the scores do not necessarily represent the students any longer. They just represent all the unique scores that were obtained from the exam. So in the event that you have duplicates allowed in a set, but you cannot impose an order, it's not ordered in any way, then what you have is a multi-set. So you can think of a multi-set as the parent collection, and then sets and arrays subsets of that. Now arrays, as we have already said, are the building blocks for MATLAB, the MATLAB programming language. And previously we looked at data types. We spoke of arrays, and we said that even a scalar could technically be considered an array, a one-by-one array. But we've worked with scalars already. Those are just numbers. So we are going to start with vectors or vector operations. Now, a vector is a collection of values arranged in a single row or It's also known as a one-dimensional array. So you basically, if you are representing an array by n, one of those n's is one if you are dealing with vectors. And usually the number of rows in an array, that's the first value, and then the second value refers to the number of columns. So a row vector is represented by 1 by n. Right? So the general form is n by n. Uh, and for vectors, you have one of these n's being 1. Right? So the first or the second, depending on whether it's a row vector or a column vector. So this is how a row vector can be represented. Now, because the first number represents the number of rows, and it's 1, you have just one row. So this is one row. If you move horizontally across, this is one row. And then it could be the number of columns could vary depending on the vector size. So this is one column, 2. You can think of it as if you were to draw a vertical line from top to down, this is one column. Then you have another column, column 2, column 3, and then column 4. So this is your fourth column, this column 4. However, you have just one row. You have just one row. So this then, the one row has already been represented here. So this will be a 1 by 4 vector, uh, a row vector, right? And the dimensions can be represented as a 1 by 4 vector. Now, on the other hand, you have column vectors, in which case you can have any number of rows, but then it's just one column. You have just one column. So if we look here from top to down, what we have here is a column of values. However, we have quite a number of rows. This is, let's use our pointer. This is one row, row 2, row 3, and then row 4. So you have one column and then 4 rows. So this then becomes a 4 by 1 vector. So the position where you have rows for the column vector, you usually have a value beyond 1. So once, if both of the values are 1, then you no longer have a vector. What you have is a scalar. Now, right from the look of this, you can see that a vector looks like this container that holds some values together, right? And a sequence of values together. And in MATLAB, you can assign this whole vector to one variable. So that is one of the advantages of working with arrays. You're able to assign multiple values or a whole range of data sets to one variable. Now, once you do that, if you were to perform manipulations or calculations on that variable, you'll be performing the same manipulation for all the elements of that vector at a go. So that really simplifies computations in MATLAB. And when you also have to generate plots, if you recall, anytime you have to generate a plot or create a plot, you need a number of values. So a simple 2D plot, for instance, would have an x-axis, y-axis, and these would be populated with there'll be a range, right, and different values. So you would have an xy pair, and all the values, the x components of all of the data points you are going to have on that graph can be placed in one vector, and then a corresponding vector for the output can also be placed, and that easily helps you plot or generate a full plot. So those are some of the key uses of vectors and why it's so convenient tool. So with all that has been said, why don't we go straight to creating vectors? Let's look at how to create. Now, there's quite a number of options to create vectors in MATLAB. You can create vectors manually by entering all the elements one by one. You can also use a number of operators, including the colon operator and the linspace function, to generate vectors within some range. that follow a rule for populating the element or the populating the vector. And then there are some built-in generators that generate some unique vectors quickly. And for manual entry, a vector is created by listing the values in square braces. So a row vector is listed horizontally with spaces in between the values. And then for a column vector, you use semicolons to move values into different rows. So we are going to try to create our first vectors, column and row vectors, using this set of values. So let's hop into MATLAB and create a vector VR with these elements. So we'll do that by come here to the command window and then VR. I'm just going to use small letters. So the square braces, you open the square braces, and then the first value was 1. Now, because this is a row vector, we create space. And then if we check values, we had 1, 6, 8, 14, 21, 45. So 6, 8, 14, 21, and then 45. So let's just be sure of that. 6, 8, 14, 21, and 45. That's great. And then we close this. So for now, I'll not suppress the output so that we see the vector being created. So here we have 1, 6, 8, 14, 21, and then 45, as expected. Now, if we wanted a column vector instead, VC, we can go the same way. The difference now is we need to place these values in separate rows instead of columns. So if we look at this, we have column 1, column 2, column 3, 4, 5, and column 6. Well, all of them are in one row. Right? So instead of placing the values in the same row, we need to place them in the same column. So all of them need to fall under one column downwards. So the way you move a value into the next row is by placing a semicolon after the first value, so that MATLAB knows that, okay, the next value is going down under this value. So then we place 6, then a semicolon again, 8. So I like to space them just so that it looks clean, but the spaces are not necessary. 14, 21, and then 45. And once I close this and hit enter, I obtain my column vector containing the same elements. Now, a quick way to create a column vector or a row vector from a column vector and vice versa is to use a transpose operator. And I will find this operator very useful in subsequent examples, because you realize that some of the inbuilt tools in MATLAB tend to create one type of vector over another, right? It tends to prefer one type over another. However, you may need the other type for some particular operation. And so being able to move from one type of vector to the other type is a very convenient option. So let's say we wanted to create VC, let me say VCC, from the row vector, right? We just wanted a column vector right from this row vector. What we could then do is transpose, we use the transpose operator. And once we do that, the VR is transposed. So we get the column vector from the row vector. We could also do that to get the row vector if we had the column vector. So we know that VCC is a column vector, or VC is a column vector. So we could just convert that into a row vector by simply transposing. And then that gives us the row vector. So the transpose operator is how you move from one type of vector to another. And all it does is just to convert your rows into columns and your columns into rows. So it applies to matrices as well. So this entire row is just, you can think of it as some sort of rotation. This entire row is just rotated and it becomes a column. You just hold this ND and pull it down. And then this whole thing now aligns vertically. So you can think of it as some 90-degree rotation. And that's how to use the transpose operator. Now, creating vectors by manual entry is rather useful but limited. And this because if you have unique values with no clear trend or consistency between subsequent values, you tend to have limited options in terms of using inbuilt tools to generate the vector. You typically have to use manual entry. And it's clear that when you have a smaller set or collection of data to handle, uh, it's easy, it's okay. But once your number of values exceeds some number, if you have to enter values in the hundreds of thousands or thousands, then you realize that this becomes a very challenging way of creating a vector. So if you have some sort of consistency between the values, or you're not necessarily recording from some source that uh, has numbers like these that may not necessarily have any consistent trend between them. There are other operators that are more efficient for generating larger vectors. And one such operator is the colon operator, or the colon operator, which comes in handy when you are dealing with equally spaced elements in a vector. Right? If you have a data set, or if you have a collection of values that are equally spaced, this operator becomes very useful too for generating a vector. So let's clear this. So let's say I have some data set, or I need some values, and I know that my value should start, or they're between 5 and 95, for instance, as just a range. And I know that they're equally spaced, like the numbers in there are equally spaced, and I know the spacing. So let's say that spacing is 2. Then I could quickly generate a vector using the colon operator by specifying the lower bound spacing and then the upper bound. So the syntax goes as follows. So let's say VCL is our vector, and then what we do is we know that the starting point is 5, spacing of 2, and then we know that our endpoint is 95. So immediately this creates a vector from 95 to 95. And then we can see that the spacing is just 2, 5, 7, 9, 11, and so on. So this quickly creates our vector for us. And the first thing to note here is the vector created for us is a row vector. And because it's large, MATLAB has to move it to the next line for us to see, but it's just one row vector. So you can see it's telling you columns 1 to through to 22 because a row vector has just one row. So all of this is supposed to fit into one row. It's just because of a small command window. That is why it has to be moved. But these are not different rows. It's just one continuous line. So you have all the way to through to 46 columns. And this is why the transpose operator becomes so important, because you can see that the colon operator always creates a row vector. And if you need a column vector, then you have to transpose the row vector. So yeah, I could say my VT should be VC1 transposed. Oh, okay. Sorry, I think this was supposed to be VCL. And that converts it into a column vector for you. Now, if we take note, earlier on when we created our first vector using the manual entry, when we looked here, let's just try one of those again. So let's say v2 equals, we had 1, 4, 6, let's say 8, 14, any number. It's just to demonstrate. So if we look here, v2, which we just created, is reported here with the in the form that we created it, right? It's reported in the form that we created it. And that's just because the vector is small, right? The dimensions of this vector, it's not a large vector. And immediately the number exceeds, the number of elements exceeds some number, beyond, we are talking 15, around 20, you quickly realize that it's not able to report it as such anymore, and then it switches to the array notation. Now, the next tool we are going to look at is link space. Now, link space, what it does is it creates a vector uh, with the number of points, right, instead of the spacing. So if you know the number of points you want to create within a range, link space is a great tool to use. And the syntax is very simple. It's link space, you specify the lower bound, upper bound, and then the number of points you expect. So this vector, for instance, creates um, 10 points between 0 and 20. So let's try that out. And we begin by specifying the lower bound, the upper bound, and then the number of points in there. And that should give us a vector. Now we may want, so let's try to get round numbers instead. Let's try to get whole numbers. So what happens to length spaces? This is essentially a closed interval. 0 to 20, the range is actually a closed range. So it includes the first digit, the lower limit, and the upper limit. So essentially, what's happening here is because of these two digits, the range here, the number of digits, or rather, let's say the magnitude or the distance being divided by the total number of points. It's not simply 20 minus 0, but it's actually 20 minus 0 in plus the 2 points, right? The upper limit and then the lower limit. So what we actually have to divide by our 10 points in this case is 22. And you realize that when you divide 22 by 10, that is how you get this increment. You get 2.2. So if you add 2.2, the increment is 2.2 for each point. So if we want whole numbers, we would have to divide by 22 by something that returns a whole number and no remainder. And that will be 11. So if we enter 11 instead, if we went with 11, then we should now get round numbers. But in that case, if you should change or increase the number of points. So link space includes the lower limits and the upper limits. And it's important to note that if you are trying to create a vector using link space. Now, aside link space, there's also log space. Let's create a vector. This creates a logarithmically spaced vector, or a vector containing elements that are spaced in a logarithmic pattern. So for instance, if we took this example, say for 1, 4, and one thing to notice, for log space, the entries or the lower and upper bounds are exponents of 10. So this is actually 10 exponent 1, and this is 10 exponent 4. So what you're asking it to do here is to create a vector with a range from 10 to 10,000. It should give us 4 values within that range. And so once we do that, we obtain the log spaced values. And one thing we want to start looking at is the values in the workspace. So we realized that when we created the first vector, MATLAB reports the value in the class. Right? So we have vec, which is the variable assigned to this vector. And then we know that it's a 1 by 11 double. So it uses array notation to tell us the data type, or the type or the value the vector holds. But then if we look at what was created by VC log during the using the log space, we realize that it gives us exactly the math notation, or the MATLAB way of representing the vectors, right? And this just happens because of space, right? So once the vector length exceeds some number, MATLAB quickly switches to the array notation. Alright, so that's just a convenient feature. If the vector is small enough, MATLAB can represent it in this form. But once you exceed a certain point, it just switches to this form. So keep that in mind. Now again, we note that linspace also creates a row vector. And anytime you use linspace, you get a row vector as your result. So if you need a column vector, again, you have to transpose your vectors. So let's just yes, you have to transpose your vectors. So you realize quickly here that VT is another variable we've created, and that has been assigned the value, the 11 by 1 double, which is the column vector. Now let's move on to the next. So we've looked at linspace and log space, and we've also looked at the manual entry. Now there are also built-in generators. Now these are MATLAB functions that are used to generate vectors and matrices, and they include zeros, ones, rand, and random. Um, Zeros just creates a matrix or an x by y matrix with all elements being zeros. So it just creates a vector matrix filled with zeros. And ones does the same, but the elements are just ones. So fills everything with one. Then rand creates a matrix or a vector with random elements. So it just creates a random vector, but the range is between 0 and 1. So all the elements are between 0 and 1. And randn does something similar, but the random elements are drawn from a normal distribution. Right? So the normal distribution determines the boundary for the range from which the randn function draws values from. So let's try some of these out in MATLAB. Let's start with zeros. Let's start with zeros. So let's call our vector z, vector z. And that is zeros. Okay, there should be one R. So this creates a row vector where you know that one, this is the notation, right? The n by n notation. So 1 by 5, which is one row, 5 columns, and that is just a row vector. So this is one row, and then these are individual columns, column 1, 2, 3, 2 to 5. So that creates the row vector. We know how to create the column vector. You could go directly and do 4 by 5, comma 1 instead, to get your column vector instead if that's what you want, or you could just transpose the first vector. So we are used to that by now. Now let's do the same for ones. So 0, ones, and you can see that creates a vector with one row, 5 columns, and all the elements are ones. So this is a pretty simple way to generate a vector with consistent elements of any type. And if you need a number beyond other than these two, you can utilize other tools like multiplication and so on to get the vector you desire. So a vector of identical elements you desire. So you can just get crafty with it. Assuming you want fives, you could create your vector VF, and that is just 5 times 1, and depending on what the length of that vector is supposed to be. So you could have 10, 1, make a column vector. And once you create that, so essentially what you've done is to create a 10 by 1 vector with ones, but because of the multiplication here, 5 by 1 is just 5. So instead of ones, you get 5 throughout. So that's just a way you can go around the limits of 5 and ones. Sorry, zeros and ones. So as you can see, this is very useful for creating vectors with similar elements or identical elements You could create very large vectors or matrices using these built-in functions. Now let's look around. So let's say we are so if we look here, we realize that VR creates or run creates a vector, 1 by 5 vector. So this the argument is just the dimensions of your vector. And if we see everything here, everything is between 0 and 1. These are all decimals between 0 and 1. And that is what rank does. Right? The numbers are random. So if I were to create another one, it's very likely the values are going to be different. Let's say I created VR again, and you realize that the values change completely. So that's what rand does. Now, because of that imposed range, you could again get crafty with the function if you wanted to change the range. So you could multiply rand by something else to shift the range. You could also move the lower limit around or the limits around. So let's start by trying to move the lower limit. Let's clear first, and then let's try to generate one where our lower limit is not 0. So in order to do that, we will offset the whole thing. So let's say we create a vector VR, and this is just random numbers between. So let's give the dimensions maybe a 1 by 5 vector again. And we know that this would essentially give us random numbers between 0 and 1. But if we wanted that to be between, say, 5 and 6, all we can do is to shift the whole thing by modifying the lower limit. So if I just go 5 plus this, what happens is every number generated within that range gets 5 added to it. So that shifts the limits from 0 and 1 to 5 and 6. Right? The interval is just 1 between 0 and 1. So that interval is maintained. And then I get this. Now we realize that because the interval is maintained, the values are still clustered between 5 and 6. So this changes the lower limit. Right? It's an easy way to impose a different limit, but it maintains the same interval. Now, if you wanted to alter something other than the lower limit, if you wanted to alter the interval, for instance, you need to come up with a different way around this. But let's say you just wanted to modify the upper limit. So what we could do then instead is, instead of adding this, we could just multiply this by whatever you want the upper limit to be. Remember, the default upper limit is 1. So if you multiply this by any number, that becomes the upper limit, because the lower limit is 0, and anything times 0 is 0. So the lower limit will just stay, but the upper limit will change. So you realize that we get more spread in terms of the kind of values we obtain. Right? We have anywhere between 0 and 10. So we're able to get this. And what happens is not this directly, it's simply run generating numbers between 0 and 1. However, after that, 10 is multiplied by everything here. So this should have been 0.959. That's originally what rand would have done. But because we multiplied it by 10, that's why we are getting these values here. So it's important to take note of that. It's a manipulation essentially. Now, if we want to change more than just that, if we want to alter the whole thing in terms of lower limits, upper limits, and the interval, what we can now do is, so we go back to our first. If we want the lower limit to be 5, now this shifts the lower limit. And if we want the interval to be, maybe we want it to be between 5 and 10, I realize that this makes sure that the lower limit is 5 by default. The lower limit is 5. But if we leave it like this, the upper limit is just going to be 6. Right? So we need to multiply this by a number. Now, if we think of the right number to multiply this by, if we place 10 here, what happens is this whole thing, the interval now becomes 10, right? So this just modifies the interval and makes it 10. So 10 times everything that happens here. But then 5 is also going to be added to it. So now what we are going to have is between 5 and 15, and that is not what we want. So we will instead subtract the lower limits from the upper limit to get the interval. So instead we use 5. So what happens now is 5 times numbers between 0 and 1. So the lower limit is still going to be 0. The upper limit is now going to be 5, right? And then the numbers are generated in between. The rest are spread in between. But now, after that, everything is going to be shifted by this 5 here. So the 0 now becomes 5. And if there was 5, that 5 now becomes 10. So this is how we're able to get um, that desired feature. It's numbers between 5 and 10. So the key here to note is the general form will be for any range you want, you specify the lower limits of that range, and then the difference between the upper and the lower limit becomes your multiplier. That's what you multiply by round. And that's it. That's the general syntax for any range you want for using rand, right? And then after that, you can modify in any other way you deem fit. Now, when it comes to rand and VN, for instance, so let's try that first. Rand n 1.5, and we see some differences in terms of the nature of the values you're obtaining. First, we are seeing the presence of negative values. And if you look at what a normal distribution is essentially, let's try to demonstrate that. So a normal distribution, right? And this is just going to be an approximate shape. I think it's going to be a bit hard using these tools to draw the true thing, but it should look something like this. Yeah, something along these lines. So this side should look like this side, but I think this does it. This should do it for our intents and purposes. This should do it. Now, usually what the center of this is the mean. The center of this curve should be the mean. So this is a normal distribution curve. We are going to make do with this. And in our case specifically, it has a mean of 0 for the random function. Now, there's the mean. So the mean is just the average. And for normally distributed data, this curve represents the data set. Now, the standard deviation, which is the typical distance any value within that data set, is from the mean, right? So the standard deviation of 1 just means typically any value is about a unit of 1 away from the mean. So the rand n uses a mean of 0 and a standard deviation of 1. So if this were, say, height of people in a class, and the average height was 170 centimeters, then the standard deviation is just roughly how far the other heights or the heights of the other members of the class are away from that mean height. So one standard deviation is simply the value of the standard deviation. So if the standard deviation is 2, then one standard deviation from the mean is 2 points to either side of the mean. If the standard deviation is 2, and we say 2 standard deviations, then we are talking of 4 centimeters, not centimeters. I mean, depending on the nature of the values you are dealing with. So if it was height, then the centimeters, it's 4 centimeters away from the mean height. Right? But I'm just going to use 4 units to generalize. Now, for this particular function, the standard deviation is 1. And there are some particular features of a normal distribution. Right? There are known features that for anything that fits under a normal distribution, about 68%, approximately 68% of the values are one standard deviation away from the mean, and roughly 95% are two standard deviations from the mean. So basically, if we were to plot, or if we assigned units to this axis, say this was 1, and if this was 2, I'm going to do same for the other side. Now, because the mean is 0, we know that the left side of the mean is negative values and the right side is positive values. So if this is 0.0, then let's try to mark that. So that's not perfect, but this will do. So if we look at, then again, this is the mean point, and because it's 0 to the left, you have negative, positive values here. And the standard deviation is 1. So when we say one standard deviation away from the mean, we are saying from this point to this point, and then this point to this point, right? And 68% of the, approximately 68% of all the values lie within this range. Then about 95% of all the values also lie within two standard deviations of the mean. And then it goes on 98%, three standard deviations, and so on. So essentially, you realize that about three standard deviations away from the mean, you cover the bulk of the data under this curve. Right? And for our function, that is exactly how the numbers are picked. So these are random numbers under this standard, normal distribution. The numbers are picked from this normal distribution exactly. And you realize that the odds of getting certain numbers increase depending on how close they are to the mean. So numbers between 0 and 1 or between 0 and 2 and -2, or rather say between -2 and +2, are much more frequent compared to numbers beyond that, right? It's more extreme values. They are possible, but they are rare, right? So the rand n function picks numbers from this curve, right, between this and this, between the ranges. So usually you see typical numbers between -4 and +4, but the chances of getting any particular number increases as it gets closer to 0. So if we look at this, we realize that all the numbers we have here are very close to 0. It's between this is -0.300. These are very close to 0, and then we have just one exceeding 1. So if we were to create that again, we'll get to different values, but we realize that they tend to cluster around 0. Most of the values are closer to 0 to the mean, and that's just because of the nature of the standard deviation. So in some cases, you get values like this, 1 of what the frequency pales in comparison to the values closer to the mean, right? Now, just as we did for rand, we can alter the nature of the normal distribution from which rand n provides the values from. So what we can do here, for instance, is to change the mean, right? And the way this happens, if we look at what the mean is essentially the middle point for the data we've been getting. And then the standard deviation is the jump. Now, this is relatively easier because the mean being the middle point makes things easier. So all you have to do is to first shift the whole thing by whatever mean your new mean is, or whatever mean you have, and then you update the interval based on multiplying. That multiplies the standard deviation. So in this case, if I wanted to create a vector, so using the rand n function, sorry, if I wanted to create a vector using this function, what I could do is, if I wanted to change the mean, I know that this is going to use a mean of 0 and a standard deviation of 1, right, to generate my values. So what I could do is to offset this by whatever number. So once I say I wanted a mean of 5 instead, well, let's not use 5. We use 5 too much, so let's use 2 or 10. Let's make that mean 10. And then we add this to it. So what happens is now the mean is shifted by 10 points. So since our mean is 10, but our standard deviation still remains 1. So we are going to get more values between closer to 10, right? A lot of values are going to be close to 10. So realize that that is essentially what happens in this case, right? The mean has been shifted. So, but since the standard deviation is still 1, most of the values cluster around 10. Now, if we wanted to to change the standard deviation as well, that becomes our multiplier in this case. So that expands the interval. So say we wanted a standard deviation of 2 instead, or say maybe even, okay, let's use the 2, then see what happens. So we realize that even though the mean is 10, now one standard deviation is essentially 2 points. So the spread is a bit better compared to the previous case where we were really close to 10, because one standard deviation away from the mean is 2 whole points. So we are talking of between minus 12 and 12. And we could even increase the standard deviation further. Say if this was also 10, then we expect way more spread. Right, you have 10, but you have numbers as low as 1, which are almost 10 points away from this, and then you have numbers as low as others as minus 1.35 and so on. Right? So you increase the range of values from which it can pick. However, within that range, it still picks the numbers randomly. So you could really get anything with this function. Now that really is it for vector creation. So after creating a vector, we may want to do other things. We may want to extract some of the elements, maybe create subsets of that. We may want to change some of the elements in there as well. We want to update some values based on newer information and so on. We may want to even increase the dimension of the vector. We have additional data that we want to include under that variable. So that brings us to indexing, slicing, and concatenating. Now, individually, this indexing is just locating elements within a vector. Slicing is cutting or breaking portions of a vector. So that's when you're trying to create subsets from an already created vector. And then concatenation or concatenating is just adding, right, appending to a vector, making it bigger. So since vectors are one-dimensional, locating elements is very straightforward. The positions are indexed, right, numerically. So the first element is position 1, the second is 2, 3, 4, and so on. MATLAB just begins from 1. So the last element is whatever that number is. And conveniently, you can also use the end statement to represent the last element. So that's a really cool feature. Now, so indexing, yes, allows us to locate, extract, and assign, and do all these convenient things with vectors without having to create them from scratch. So let's start with indexing and slicing. Now, if you have a vector and there are a number of elements in there, you realize that the first vector or first element here is position 1. This is position 2, 3, 4, and 5. So those are the indices, or that's the index for the vector. And the syntax is just to uh, indicate the position or the index of whatever element it is you want to modify. So we locate elements by their position. So VR, you pass the argument, which is the index to that, and that should extract the third element for you. So let's practice some of this. Let's create our own vector, and let's use the colon. So I'm going to use the colon operator to let's say the step size. Let's make that 2 as well, and then let's get all the way to 20. And so this creates our vector for us. Now, say we wanted to identify what was in the fourth position. It's simply VC and 4, and realize that element number 4 is 8. So that quickly returns that for us. So that's just the indexing. You can use this. So I could go VC1. That gives me the first, which is 2. I could go VC end, especially if you have a very long vector and you don't know all the elements, you could use this, and that will give you the last element in the vector. If you know the number 2, you can just specify it. So that's very cool for this. Same thing applies for a column vector. also indexed by position in that same way, numerically starting from 1. Now, if we want to extract a range of values, we could do more than that. So we could go VC, and then say we want to extract the values from position 2 to position 5. So we could just go 2 to 5, and that gives us from the second, third, fourth, and fifth, right, elements. So that is how to use a range. Now there's actually a step size here, but because we did not specify, it assumes a value of 1. It just moves to the next one. Now we could, so let's first expand this. Let's go for the 7th position so that we get a few more values. And we see that these are just subsequent, they are just sequential, or they follow one after the other, right, all the way to 14. And spaced with 1. Now, if we wanted a different spacing, we could specify the spacing as well. So maybe we don't want it to jump over every other number. Then once we do that, you see that it starts from 4, but instead of going to the next, it skips and moves to the other one, which is 8, and then it does the same and gets to 12. So that is how to use an interval to get a different spacing or to extract within different space. We could also just extract the vector directly, so we could go VC and we'll just indicate those positions. So I could go for specific positions in there. I could go for the second, maybe the fifth, and then the eighth. That is if I have them. And that should give me those ones respectively. So if I go to my vector earlier, or I could extract anything essentially. I could go for first, sixth, and then last. And that should still give me the values as I want. So this, if we see very much, is extracting what we want. So you could do a lot with this indexing. I could say maybe my first, I want to extract from my first to the last, but 1. I should have used VC instead of real. Sorry, this should be VC. The vector name is VC. I think I got that mixed up. So I can extract from the first to the last but 1, and that just omits the last one. I could, so it's VC now, take from the first, or maybe let's reverse. Let's rather go from the end to the first one. But now if we are going to specify the steps, I think it has to be negative. So let's put that, but let's run this first and see what happens. 1 by 0 empty double row is so that does not work. There has to be negative steps, and because it's a value other than 1, we have to indicate that to MATLAB. So this should be -1. It's moving backwards, right, from the end forward. So this assumes that it's starting from the end. What we did earlier, starting from the end, which is the last element, and then it's trying to move forward, but there's nothing there. So it just says it's an empty double row vector, right? It's empty. So what we want it to do is to count backwards, and that is a negative step. So we put the -1 there, and that should work. It obtains the last element first, and then goes back till it gets the first in our original vector. Now we've not created a lot of variables, so let's just clear the command window. We still have our vector here, remember VC. So first let's just call it so that we have it, and let's try to modify the elements in there. It's beyond just indexing. So say I wanted the third element to be something else. Say I wanted that number to be 5 instead. I could just set it to 5. And once I do that, VC is updated, and we realize that instead of 6, as we originally had here, we now have 5. And that is also updated here. 5 is now the third element. So that's one quick way to modify individual elements. You can also use the range, as we saw earlier, to modify quite a number of elements at a go. So say I wanted to modify the 4th to 6th elements. So VC, I could change 4 to 6. And those elements are element 4, which is this, all the way to this. If I had a new range in mind, I could just enter that 7, 11, 10, and that will just modify that section for me. I could also delete elements, and a simple way to do that is to access that element. So I could go for the third element, and I just have to set it to an empty set. And once I do that, that element goes away. So if we check, our last vector had element 5 in the third position. Now that whole position is gone. So what happens is our vector is also shortened, and we have fewer elements there. That position eliminated, and 7 has taken the place of 5. And so we have one fewer column, one less column, right, in our vector. Now let's talk about concatenation. So vectors can be appended. You can create a larger vector or matrix by appending, right? And to add members, you can first access the last position, right, and just move on from there, as we've seen with the end statement. We could also just create a bigger vector and then include all the elements at once. So there are a lot of ways to concatenate vectors, and you can be crafty about the whole thing. So this allows us to take note of something very early. We realize that for any given task, there's quite a number of ways to go about. Sometimes you have a number of options to achieve the same goal. And as time goes on, as you build competence in the language, you realize that some parts are more convenient and easier to use than others. So that is how you build your own sense of code structure and how you go about things to be able to build programs more efficiently. So take note of the alternate ways, or all of these alternate methods that we use. And as time goes on, you find out that some of them give or present some advantages that others do not in specific situations. So the most important thing is to understand the general concept rather than to try to memorize all the syntax, because it only increases from this point onwards. So for instance, for vectors, the key thing to note when it comes to all these modifications and stuff is that the elements in there have positions attached to them, and those positions can be indexed. It starts from 1 all the way to the end, which is the last one, and then you move on from there. You can access things, you can modify elements, you can add onto it. So really, code structure or an understanding of algorithms is much more important than memorizing syntax, because there's a lot of tools for obtaining syntax for anything if you know exactly what you want to do anyway. So it's more important to know how to engineer your programs rather than um, uh, trying to memorize all the syntax available. So let's start with our already created vector. VC we still have here, and we are going to first try to append by indexing. So VC, we go over end +1, and you say we just wanted to add 45 to this. So once we do that, realize that yeah, it's added to it. We could go further. And if we wanted to use more values, we could do that. I could just copy a part of this. So n+1 to n+4, that should be 4 values. I could just copy some of this and place there. And that should add them onto. So the end was 45. So the next position is that, and you can see that this vector is just placed here. I could also create another vector. So let's say VC2 equals, and let's just take some random portion of this. So let's take this part, and I'm going to use that to create my new vector. And if I wanted to merge two vectors, a simple way is to create a third vector. If I didn't want to enter the elements manually, or if I wanted to have the original vectors as well as my new vector, then I could just do this VC and then VC2. So you notice that the size of the vectors are similar, right? These are both row vectors. That is why adding horizontally is possible. If this was a row vector and this was a column vector, this would be a problem. Adding it the way we just did. So you have to take note of the nature of the vectors before you add, because if this was a column vector and you try to add it to this at the end, you have all these other columns that are not satisfied. Right? All these other columns are supposed to be filled and are blanks. And likewise, in the other direction, if this was a column vector, you try to add this row, you create additional columns with no entries below them, right? So you are likely to run into some problems in that case. So just as you can append, you can also prepend, right? We create a fourth vector, and now I can place something rather before. I want to add the element 50 to VC, and I'll put something in front of VC. Now, the last time you had VCs here, so we can see that a 50 has been placed before, and every other thing applies. Now, let's look at column vectors. Let's take a column vector example, and then see how some of these incompatibilities can cause problems for us. So let's clear all of this first. Now let's create new vector, say v1. Let's say that had 1, 2, 3 elements, and then I'm going to suppress it, but at least you can still see the values in the workspace. Let's create v2, and then that should be 4, 5, 6. Now these are both going to create row vectors. So let's try to create a third one by appending and then see what happens. Now, so first let's append them horizontally. We have v1 and v2, and right, that just extends our vector for us. Now let's try to do horizontally v4, and that should be v1 semicolon v2. Remember to move it to the next row, and we see that because the dimensions are the same, this can essentially sit under this. Right? The v2 can essentially sit under v1. But what is happening now is we no longer have a vector; we have a matrix. This is a 2 by 3 matrix, 2 rows. So this is row 1, this is row 2, and then these are the 3 columns, 1, 2, 3. Now let's say the vectors were very different, right? One was a row vector and one was a column vector. So let's create, no, I think I want to define. So let me create a vector VC1 instead, and make this a column vector. So I'm just going to copy V1. Right. So 1, 2, 3. And once I create this, we check VC1 here. It's a column vector. Right? So if I didn't suppress it, maybe I should remove the suppress so that we see that it's this. And then let's try to append. So let's try to add it to V2. So we create a new vector. Let's say VM5. And then let's try to append them. So VC1 first, and then V2. Okay, this is fine. And realize that we run into an error. Dimensions of arrays being concatenated are not consistent. And if you look at VC1, this is a vertical or a column vector, and then V1 or V2 is a row vector. So if this were to be appended in any way, you realize that you end up having blank entries or blank spaces, and that cannot work. So this combination is not possible. If you alter it in any way, you still realize you run into the same issue. So we could start with this comment first, and we run into the same problem. So the two vectors have to be of the same dimensions, right? If it's a row vector, you can append or concatenate multiple row vectors, but not a row and a column vector. Now let's also try to look at the sizes. So let's say we had V1, which we still have. Now let's create V2M, and now this time we are just going to include 2 elements, so 4 and 5 in there. So that creates V2M, and then let's try to append horizontally. That should be very possible. So let's just call this VF. And then let's say the elements were V1 and then V2M. Now this should work fine because it's just adding on. Let's try to put it in columns as well and then see what happens. So instead we have VM, we place a semicolon, and then we run into a problem. And that is because if you try to place this, so V1 is 1, 2, 3. Right? V1 is just 1, 2, 3. And once you try to place V2M, it's supposed to come underneath this, right? In this format, it's supposed to come underneath it. So you have 4 taking this first position, filling the first column, 5 being the second column, and then the 3 has no entry below it because there's nothing else to place under it. So you end up having a problem, an incompatible concatenation, because the resulting combination or the resulting array is not really an array at this point, of in any meaningful form. So unless that spot was filled with something else, right? So MATLAB just returns an error telling you that the sizes are not consistent. So that's it for concatenating vectors. There'll be a few more interesting examples in the assignments you can try out. Now, the next thing we want to look at should be logical indexing. And really, indexing using logical statements or comparative operators, it's also very convenient to access a range of values within a vector. So rather than accessing vector elements based on position, we can use conditions to access elements that meet some sort of criteria. So for instance, we have this temperature vector that records different temperatures. And if we wanted to extract all the temperatures meeting a certain condition, in this case, all the temperatures above 300, we can do that, right? And this represents a logical index. So MATLAB quickly samples your vector and then checks which of these elements meets the criteria, right? So what you essentially have is a logical mask, and you can get that logical mask if you just wrote this in the real form. So let's maybe I'm just going to copy this into MATLAB. Uh, so it should be this instead, and that creates a vector. So I could go T greater than 300. No, that's a small t. And what is returned is a logical array. Now, this logical array is a truth mask, right? If we look at the positions, the first element here does not meet the criteria, is below 300. So that returns a false output. And the next one meets the criteria, 310 is greater than 300. So that's true, false, and so on. So this is a logical mask. If I wanted the actual values, then I have to actually extract it and reference the original vector. So I could do that with T and then specify the condition as the argument. So T is greater than 300 to tell MATLAB that I'm actually trying to extract the values that meet that condition. And that then returns those values for me. 310, 340, and then 320. Now I could also use the find function to get the indices if I'm looking for the positions. I don't consider this to be as useful as the previous one, but it also has its uses. So if I needed the positions themselves, I could use the find, and that returns their position. So this is position 2 is 310, the fourth position is 340, and then the sixth one is 320. So it's just these numbers, but I have the indices now. And I could use multiple statements if I needed something in a closed interval. So I could go to extract, then first T, I need values below 3, let's say 310, but I also need values above 280. And we realize that only one value meets that criteria, and that is 295. So I can also use that to tighten my range more. And that very much sums up logical indexing. Now, some of this may look math heavy or may appear to be of more math utility than anything, but you realize later on when you perform certain calculations, for instance, and you want to extract a particular portion of your results for plotting or for subsequent processing, you find some of these very helpful at that stage. So we just want to get some of them out of the way there before we get there. Now, next, we are going to look at a number of vector operations. Now, for vector arithmetic is simple, straightforward in MATLAB. You only need the vectors to have equal sizes or to be compatible. So you can simply add vectors. I'm going to copy this. Going to MATLAB. So this is A, and this is B. So we could go A plus B, and that just adds 10, 10 plus 1, 11, 22, 33, and so on. We could also go A minus B, perform subtraction. Let's create a third vector C for different reasons, just for demonstration. So that vector also exists. Now let's try A plus C, and then we run into this problem because of the incompatible sizes. So this is 1 by 4, this is 1 by 5. So that's just not possible in MATLAB. Now one may be wondering why MATLAB doesn't just add them and then place a 0 there for the elements that's missing, and or just place another one there. That's if you realize that the positions and the individual values in arrays tend to have meanings, you quickly see why that is a problem. Because even if you place 0 there in place for the empty spot, you're actually saying someone, if it was a test, you're actually saying someone took the test and scored 0, and that is not what happened. So there's even the 0 there has meaning, and that's why you cannot just place that in there. Now, when it comes to multiplication of vectors, we have to be careful because vectors and matrices have special uh, operations that mimic multiplication or products. They have a number of products. So it's not just the arithmetic products. Vectors, for instance, have dot products, outer products, and so on. And those can give quite different answers from what one will intend to do with arithmetic multiplication. So more commonly, you would want to go element by element, right? If you have two vectors and you were in internal multiplication, you want the first element to multiply the first in the other vector, and so on, right? And that is array multiplication or element by element. And you need to specify that when you are multiplying. Now for scalar versus vector multiplication, that's very simple or straightforward. The only way that can happen is in array form. So if we come here, we have our vector A. If we created a vector D, and that is just 2 times A, then we realize that just does, by default, it's an array operation. It just multiplies them element by element. Now, if we wanted to multiply A and B, let's say we call the vector F, and that was A times B. So this is what we're talking about. This multiplier here can mean anything. There are a number of product operations vectors can actually undergo. So if what you're looking for is for 1 to multiply 10 and 2 by 20 and 3 by 30 and so on, that is element by element. It's element by element multiplication. And you do that by placing a dot before the product sign, the asterisk, which is the multiplication, so that you get the desired output. So that is the array operation. And now the same thing applies to any multiplication based operation, right? Division is also multiplication based. You can think of it as the product of something in the inverse of the other. Right? And so if I wanted to divide B by A, and let's call that H, that just B dot A. and I get all of these divided by subsequent ones at 10. So this also applies to division, and then exponents, right? Powers are also multiple products. So in the same case, if I wanted to raise this to any power, I need to sort of say b, and rather do that to the power a. But if I went the other way around, the values could have been huge. And this is also an element by element operation because of the dot here. So remember, if you want element by element operations, you need to indicate using the uh, dot symbol. Or let's call it the dot operator or arrow operator. Now, because there are also other products, one of them, for instance, being the dot product. So if we are just going A times B, this is a 1 by 5. This is also 1 by 5. So A times B is 1 by 5 by 1 by 5. And that is a dot product. So that should result an error. And the reason for this is actually interesting. Um, Now, the way the conversion of row and column vectors in MATLAB is not strict mathematics. In math, vectors are vectors, and the elements and their orders matter, right? Rather than how it's oriented on a page or anything of the sort. For vectors in particular, so A and B could be multiplied in a sense, right? If they were just vectors written on a paper, it does not really matter. You could multiply them. Now, what is happening here is, by that I mean the dot product or anything or any other thing of the sort. Now, what is happening here is MATLAB works with matrix operations. So when you multiply this, that is why it needs to even write the vectors in that array format or the matrix format. So even it's in that case, it's differentiating column vectors from row vectors because it's looking at the whole thing as a matrix with one row, and so this number of columns, or one column and this number of rows. And now when it comes to matrix multiplication, there are strict rules. So you can only multiply matrices with similar or identical inner components. For instance, you can only multiply maybe a 1 by 3 matrix by a 3 by 1 matrix, right? The inner components or the rows of one and the column of another has to match. So what happens here is when you look at this, this is a 1 row 5 column vector, 1 by 5. This is also 1 by 5. So when you do A times B, you're multiplying 1 by 5 by 1 by 5 because the inner ones do not match. Let's try to write that so that it becomes clearer. So according to the rules of matrix multiplication, you need to match inner dimensions, right? So a 1 by 5, 1 by 5. Now, if you are going to multiply these, now these are the inner parts, right? This and then this. Now they need to match for matrix multiplication. So what you could have done is multiply 1 by 5 by a 5 by 1. Then in that case, you have identical inner elements, and that is how MATLAB then determines what to multiply by what. So it follows strictly the rules of matrix multiplication, and you realize that if you are looking at vectors at one-dimensional matrices, then it becomes clear why MATLAB is not able to compute this. Right. So in that case, it returns an error and suggests array operators. So the key thing to note here is these operations carried out on vectors and matrices are not necessarily made for vectors. They are matrix operations. And then a vector is a special case of a matrix where you have one dimension, right? One of the you just have one of either columns or rows. So if you want to perform dot products, you need to manipulate your vectors in a way that they obey the matrix rules, the rules of matrix multiplication, but then they still give you the result you want, right? The operation you are looking for. So in this case, if I wanted a dot product, I would need to transpose one of these. and I multiply it in such a way that I obtain the dot product. So in this case, if I want to multiply A by B, if I transpose this, it now becomes a column vector, which is 5 by 1 instead of 1 by 5. And then I have 1 by 5 times 5 by 1. And that collapses everything. So you realize if we look at what we were doing earlier, if this now becomes a 5 by 1, then the inner components are compatible and then it collapses. Then you just have a 1 by 1 um, array or matrix, which is just a scalar. Right? That's just a scalar, as a zero-dimensional matrix. And that is the product of the dot product. That's the output from the dot product. You obtain a scalar. So if I wanted the dot product, that is what I'd have to do. I'd have to go for A times the transpose of B. And that should now give me the dot product of these two vectors. Now, I could also go with the other way around, because I had 1 by 5 times 5 by 1. I could also go 5 by 1 times 1 by 5. So in that case, you notice that the inner dimensions is 1, or the inner part is 1. And then you have the ones collapsing, and then you end up with 5 by 5. Now, 5 by 5 is a matrix. It's a matrix with 5 rows and 5 columns. So that is the outer product. So how you orient the vectors will determine the nature of the computation you are carrying out. So if I go A, even if I transpose B first, and then I multiply that by A, I get a completely different result. I get a 5 by 5 matrix. So it's important to take note of these things as we progress. So really, there's when it comes to multiplying vectors and these other product operations, you usually look at multiplying vectors of different dimensions or orientations. So you multiply row vectors by column vectors. In the case, especially when you are not dealing with array operations. And this is important. Column vectors are actually very important when you are dealing with a system of equations, system of linear equations or matrix operations. A lot of the one-dimensional results for variables are reported in column vectors. So those ones, it may appear as if we are under exploring them, but they are actually very important in MATLAB. So just as we discussed, we have A times B, which is the dot product, and in this case, you just need to take a look at the dimensions to know which of the products you are computing. Now, in the case where you add a row vector to a column vector, that is just undefined in math, because remember, math does not differentiate in vectors. Vectors are just vectors, right? And that orientation is because MATLAB is actually representing the vector by a matrix, right? And the vector is actually a special case of a matrix. So that's where the idea of a column and row still comes into play. Now, what happens when you try to add a column and a row is interesting. It results in an outer combination and known as broadcasting. So in this case, each element in one vector is added to every row in the other vector. So if you take this element, for instance, 1 is added to this, 2, and then 3. And then 2 is also added to all of them, and 3 is also added to all of them. So what happens next? You can essentially start from the column vector. You could take this first, and if you add 1 to 1, that is the first entry. Now, 2 is added to 1, that becomes the second entry in the row that belongs to 1. And then 3 is also added to 1, that becomes the third entry. And the same thing is repeated for the second element here, which is 2. Also, 1 is added to 2, 2 is added to 2, and then 3 is added to 2. And that fills the next row, and then that's also repeated for 3. So you have a 3 by 3 matrix in the case of this addition. So you can try it out. Example is here, and you see that adding that up just gives you a 3 by 3 matrix. Now, the other vector functions to look at. Now, these functions allow you to determine certain properties of a particular vector. So there's length, sum, mean, and quite a number of them. So length tells you the number of elements in your vector, length v. So if we go back to our previous example, we could take any of these vectors we created. And if we go back to HD, realize it just has 5 elements. So that tells us the number of elements in our vector. We could you check the sum operator, mean, minimum, maximum value. We could sort the vector in ascending order. We could compute the cumulative sum. And then now there's also the dot product. So if you remember, we computed the dot product and we had 550. So let's just do that again. I think that was A times B transpose. And that gives us, that was the dot product. So this is a quick way to verify that that's A, comma B. Now you can decide not to transpose. The reason here is the dot is like essentially a vector operation. So MATLAB now knows that, okay, you are not just multiplying, you're actually trying to carry out a dot product on these vectors. So the dot product is a reserved vector operation. So then you do not need to transpose, and it understands that is the mathematical operation you are referring to, right? But when you try to go by multiplication, you have to make sure that the matrix rules of matrix multiplication is obeyed, and the two are numerically equivalent. So learners, that brings us to the end of this lesson on vectors and matrices. Today we've looked at vectors totally. In total, we will switch to matrices in our next lesson, hopefully. Thank you for your time. I'll see you in the next lesson.